Z-transform is exactly the same as the discrete time Fourier transform, except in addition to the e to the minus I omega n term, we also multiply it by an r to the minus n term. R is a positive real number, and when you raise r to the exponent negative n, you get an exponential curve. And when r is less than 1, the curve increases exponentially. And when r is greater than 1, the curve decreases exponentially. So we can sort of think of the Z-transform as a function that is looking for the correlation between the discrete time signal and both sinusoids from the E term and exponentials from the R term. And if we combine these two probing signals together and simplify it a bit by pulling out the negative n exponent, we get R times e to the I omega, and all of that raised to the minus n. And now we can just claim that a new variable that we call z equals r times e to the I omega, and we've reached the definition of the Z-transform. Now, why is this important for understanding the system itself? Well, if a system can be modeled as a linear shift invariant difference equation, then we can guarantee something about the response, namely that the output will contain both frequency content and exponential content, because the solution to a linear shift invariant difference equation contains both of those components. And if we understand the frequency and exponential makeup of the response given a known input, then we can know exactly the system that generated that response. I mean, imagine if the impulse response of a system looked like this pure exponential decay. It doesn't really make sense to transform this with a discrete time Fourier transform. I mean, we are going to get frequency content, but it doesn't really mean much because it's not actually representing the dynamics that created this signal. Ideally, we would want to know that there are no oscillations in this signal. There's no important frequency content, but instead it's just a pure exponential decay because we know what kind of a linear system produces an impulse response that is a pure exponential decay. So, if we're looking for exponentials in the signal, it might make sense to approach this problem just like we did with the discrete time Fourier transform. That is, let's probe this signal with different exponential functions and see if we can determine which exponentials exist within the signal. And mathematically, this is what the Z-transform is doing. We're probing the data signal with both e to the minus I omega n and r to the negative n to see how well correlated it is to different combinations of oscillations and exponentials. But this simple additional term, r to the minus n, adds some new problems that we didn't encounter with the discrete time Fourier transform, namely convergence. For example, let's take the exponentially decreasing impulse response, and let's set omega equals 0 in the Z-transform. And so we're really just multiplying by r to the minus n, and then summing the result. When r is greater than 1, then our probing signal also decays exponentially. And if we multiply these two signals together, we get an even stronger decay, and the sum is just some finite value. It's not very important what this number is. But as we start to decrease r, the probing signal starts to decay less quickly. The product of the two is also decaying less quickly, and so the summation is growing. It's still just a boring finite number though. But at some point, the probing signal grows at the exact same rate that the time signal decays. And when that happens, the product is just a perfectly flat line, and the summation right at this point becomes infinite. It no longer converges. It is this infinite value that tells us that we have perfectly matched the exponential. There is a pole here, since the summation reaches infinity. And in this case, the pole is at a value r less than 1, which means that this is a stable system. You know, the energy in x of n exponentially decays over time. So the Z-transform is really just sweeping through a bunch of different frequencies and exponentials to see where the summation reaches infinity, called poles. And it's also looking for where the summation is 0, called zeros, but we're going to talk more about poles and zeros in the Z-domain video. Alright, so this is all good, except that there's a small problem that can cause confusion. If we keep decreasing r, then the probing signal grows faster than the time signal decays, and the summation is, well, still infinity. In fact, it's even more infinite, which I know doesn't make any sense, but you know, it's growing faster. So we can't really make the claim that the interesting result only occurs when the summation doesn't converge to a finite value. It's only right at the moment that we go from convergence to non-convergence that gives us insight into which exponentials exist in the signal. So this region of convergence is important because outside of the region, the results don't make any sense. And this actually becomes an issue if we want to take the Z-transform of finite discrete data. If we only have finite data, then the summation will always converge, except for maybe at z equals 0 and z equals infinity. I mean, even in this example, if our data only has these 20 samples, then you can imagine that this summation of this blue line here is very much not infinity. So we can't tell if we've matched the exponential content of a finite signal by looking at when the result goes to infinity. That is, unless we make an assumption about what the data is doing for the rest of time. Remember, at the beginning, we did take the Z-transform on finite data, but in each case, I made an assumption about the future data, namely that it was 0, or it was constant. Without that infinite data, the Z-transform just isn't as useful as the Fourier transform. In fact, this is why in MATLAB the fast Fourier transform function can operate on finite data. But there isn't a corresponding Z-transform function that will do the same. The Z-trans function requires a system model in order to have an understanding of that infinite data. But despite that limitation, the Z-transform is still really powerful compared to the discrete time Fourier transform. With the Z-transform, we're analyzing the system that created the data by looking at frequency and exponential content. With the Fourier transform, we're analyzing the signal that the system produced, and we do so just by looking at frequency content. All right, I hope all of this information has helped you understand the Z-transform.